Hi guys, welcome to Minds of Machine. Today I am going to show you how to build the Lingua Flow, a powerful multilingual text-to-speech application using Facebook's model, that is MMS-TTS model. In this tutorial, we will create a complete application that can convert the text to natural sounding speech across multiple languages, and we will be focusing on the English models to start, but we have also added Spanish, German, French and Hindi to it. And I will show you how to extend this supports in other language also. But in this tutorial, I will be showing you how to build the basic core structure or the backend part for this particular application, which you can see in the screen, and also how to connect it to your front end. So this tutorial will cover only this part. If you want to know about how to build the front end part, do comment in the comment section UI and I'll create one more tutorial for it. Before starting with the code, I would like to show the demo of how this application will work. So as you can see, I've entered the text. Now I will change a language here to Spanish and tell it to generate a text speech. And what it will do is it will generate a speech in the form of audio
Bienvenido a
files.
Linguaflo. Esta aplicación multilingüe de texto a voz demuestra el poder de la síntesis de voz de moderna. Observe cuán natural suena la entonación, con pausas apropiadas y énfasis en diferentes palabras. Esta tecnología puede ayudar a hacer que el contenido sea más accesible y atractivo en las barreras del idioma.
Now I would also like to show you in French how the same text is spoken.
Bienvenue à LinguaFlow, cette application multilingue de texte vocal démontre la puissance de la synthèse vocale de l'IA moderne. Remarquez à quel point l'intonation sonne naturelle avec des pauses appropriées et l'accent mis sur différents mots. Cette technologie peut aider à rendre le contenu plus accessible et à engager dans les barrières linguistiques.
Now let's start with the development part. So see you in the coding section. Now let's understand the requirements for building the project. So first we are gonna import in the requirement file, we are gonna define the Flask equals to 3.0.2, which means Flask is a web framework that powers the entire application and it handles the HTTP request and response routing, the core web server functionality. It is required that without Flask we could not create a new web API with the endpoint for translation and speech generation for our project. Then next we are gonna need the Flask core, which is the version of 4.0.0, and it is required for the cross origin resource sharing that supports Flask. So it allows the API to accept requests from web application hosted on different domain, which is essential for front-end application to communicate with this API, or else you won't see the response as required. So usually we use CORS for the API purposes. Next, we are using the Python environment of version 1.0.1, and the purpose is to load the environment variable from an environment file into the application environment. So this is required to enable the secure configuration by keeping sensitive informations like API key out of the source code and version control. As we are using the Hugging Face model over here and certain other models to for which we will need the API key, that's a reason I've used Python.environment to keep my API key information inside that. Then we would need transformers, which of version 4.38.2. The purpose is to use the Hugging Face transformer library, which provides pre-trained AI models, which we are going to use for our text to speech model, which is trained by Meta. Next, this core library. It powers the speech synthesis functionality, and the version constraint ensures compatibility with the specific model being used. Next, we are going to use Google Translator of version 3.1.0a0. The purpose of this is to translate whatever response we get from the model into different languages. So, it handles the text translation functionality. Note that this is a alpha version, which may indicate it's using newer Google Translate API feature but might have some stability issues. Next one we are using is the Torch library. The PyTorch is a deep learning framework used by the transformer model, and this VITS models are built on PyTorch and cannot function without it. No version is specified, meaning the application we will use, whatever version, is compatible with the installed transformer library. Next, the SCIPY is a scientific computing library that includes audio file handling, while used specifically for converting the raw audio waveform into proper wave files that can be sent to the client. Like Torch, no version is specified, allowing for compatibility with other dependency. These dependencies work together to create a complete system. And Flask provides the web server cores, enables cross origin requests, and .env manages configuration transformers, and Python Torch handles the AI model. Google Transforms provides translation services, and assigns py processes the audio output. So these all library software will be required for building our text to speech meta based application. Now let's understand the core backbone of this project or application which we have created. So I've created a folder called TTS backend folder, inside which I have set up the virtual environment for the Python, because the backend is written in Python for our project, and the entire logic I'll be writing within the file server.py. So in server.py, first we have installed all our requirements which I had mentioned before this. So first we will be importing the libraries like Flask, request, JSON file, and send files from Flask. And these imports are essential for building a web API. Flask is the web framework. Request handles the incoming data, and JSONify formats the API response, and send file enables the audio file delivery. The major reason why it is required is without these files we could not create API endpoints, process the request, or return the response. Now next we will be importing the Flask cores library and import the cores from that Flask cores file. The major reason, the purpose of this is it enables cross origin resource sharing to allow requests from front-end application hosted on different domains, and without cores, browser would block the request from front-end application on different domains due to security restrictions. After that we will import the WITS model auto tokenizer from transformers. So this provides the text to speech model and tokenization capabilities. The major reason why it is required is the core component that converts the text into speech waveforms. Next we are going to import is translator from Google Trans, and the requirement is to provide translation capabilities. Why it is required is to enable APIs to translate text into different language before generating speech. After that we are going to import is Torch. The purpose of this is it provides deep learning framework needed to run the TTS models. The major reason why it is required is the Hugging Face models are built on PyTorch. Without it they cannot function. Next we are going to import is spy.io.wave files. It handles wave audio file formats, reading, writing, and it is needed to convert the raw audio data into proper wave file and formats that browsers can play. Next we are going to import is the OS. The OS is a variable. Along with that, we are going to import is load dot environment from dot environment. This basically manages the environment variables, input output handles, in memory file operations. Environment variable is required to store the API key, security, and input output enable in memory file handling without writing to disk. Next we are gonna now, after importing all the required libraries, now we are first loading our this one, what do you call as we are gonna load the environment variables. So in that we are going to write it as load underscore dot env bracket round bracket open, round bracket close, and the load environment variables forms a env file which I have already created. So I'm basically going to access my API key through this particular function which I have written, so that my model, whenever I'm passing a request to it, it knows that I have the API key and this is the API key which I'm going to use. Next, it is a very important practice to use .env files, because it keeps the sensitive configuration data like API key separate from code for security. Next, we are going to initialize the Flask application. Then we are going to define CORS for all routes. The major requirement for this is to create the web application instance and ensure that the front-end clients can communicate with it. So we are just creating an instance for our application and also allowing our front end to communicate with the backend, so that it doesn't reject the request. After that, we are going to initialize the translator. So creating as we are going to translate whatever response we are going to get from our model into a speech of different languages. So I have used the Google Translator client, and it why it is initialized is because the translation service wants for reuse across multiple requests and also improves the performance. Now we will map the language code or for the Google translation. So the purpose of this is to map the language code to the model ID and translation code, and it also creates a single source of truth for language mapping, making it easy to add or modify the supported language. As you can see, for English I have written English, and then I have created then I have written it as model, and I'm using Meta's model for English. And then I am also adding the translation code for it as en. Then I have created one more for another language, that is DEU, and again I will be adding the translate code for it as DE. So the models whichever I am referring are the trained model by Meta, and that we are going to use for our purpose to build the text to speech text to speech conversation application. So Next is for the French one. So I've used the French model, and translation code, I'll give the first two letters of the ID. Same way you can add multiple of them, since mine has Spanish, French, Hindi, English, German. So all those things, for all those languages, I've added the models in the language model. Once that is done, next we will be doing is creating a cache uh, to store the loaded models and tokenizers. This is required to load because loading a model is expensive in time and memory. Caching prevents reloading for each request. So that's the reason we have created a cache. Next, we will be defining the function of get model and tokenizer, and through to this function we will be passing the language, and this function is to access or load the model, and it also centralizes the model loading logic with caching for efficiency. So we are gonna then check if the model is already loaded, and if it is not, then we will load it, and we will also prevent redundant model loading, which will save the time and resources. After that, we will be low if it is not loaded, we will first get the model ID from the language model which we have defined. Then just for the purpose, I've just printed the output to see whether I'm getting the response or not, and then I will define the model cache which I have defined in the previous step, to where inside which I will be passing language as index. Inside that cache, I will be storing the model by getting the pre model ID and also get the tokenizer. It is basically to load and cache the model if it is not already loaded, and and to initialize the model from the the property initializes the model from the pre-trained Hugging Face repositories and adds them to the cache. Then we print. This is basically to see the output whether the model is loaded successfully for the particular language or not. Once that is done, we will return the requested model and the tokenizer in the form of return model cache language and the model, and also return the models cache for language. So these are the two things which we will return along with the tokenizer. So the return, it basically returns the requested model and the tokenizer and provides access to the loaded model for TTS generation. Now after that, we will be defining the translation API endpoints. This basically creates a URL route that client can call to translate the text. So at API root dot root, and in the bracket you can see the request is of method post, and the URI slash API slash translate. Then we are going to define translation API's endpoint to create a URL route that client can call to translate, and below that we are also going to create a function which is translate the text, and inside which we are going to extract and validate the request parameter. This is basically to safely extract the JSON data with default to prevent error. So we are basically trying to extract the data here in a very secure manner for whichever language we have selected. Since the model will be mostly in English, so we have passed the language as English in it. If there is no text input provided, then we just provide a validation saying that uh, prevent processing empty request and return the appropriate error code, so that when we build, we basically know what has gone wrong, whether we have given the input text to the model or we have not given any input text, so it will throw an error. Next, we will also check if the language model is being supporting or not. That is, if that particular model which we have declared in our language model has some error, then it will throw 400, and this also ensures we only process the languages we have model for, so that we are validating it. After that, we are translating the input text to the targeted languages. So this performs the code translation function of this endpoint, where we are defining creating translator.translate function, inside which we will be passing text and the language model which we have defined in our language model structure. If we want it in English, then it will convert it into English statement into English. If we write a statement in English, and if we want the model to speak in German, we have to pass the model in German text. So that's the reason we have basically written the translate text API, and this is basically the Google API which converts English into different languages. And then we are gonna return the response in a JSONify format which we had imported previously. We would get the translated text and original text also in that, and we will return both the translated and original text and provide a complete response with all relevant information. Now we are gonna raise an exception in case of there is any we are going to do the catch and handle the error gracefully here. That is, if we find any errors in our translate.api, then this try catch which we had defined, I have written an exception that it shows if there is an error, then it will show the what is the error, along with in a very by you applying JSONify to the error response. And it also helps you to prevent server crashes by catching exceptions and return informative error messages. So that's why try and catch is very important when you write the function. Then the next, I'm just formatting the as formatting my code so that there's no issue and they are correctly meeting the rules of Python. So as you can see, there are some errors in the format. I'm trying to solve it. Next, we are going to write our main function, that is text to speech API. This is the main thing which this application is doing. So first I'm going to define an API at API root, and this function can be accessed by /API generate speech, and the method which it will be using is post. The purpose is to, as we know, is to text whichever it gets, it converts into speech, and in and it's an API endpoint for that, and it also creates a URL route that the client can call to generate the audio. Then we are going to define the try and catch, as we know why it is required. inside that we are going to first define data is equals to request dot get json file. Then we are gonna get the text is equals to data dot get text comma dot stripe, and then we are defining the language which we want. We're trying to get the language for the data, and finally should we translate for that particular language, if it is yes or not. So we are basically trying to extract and prepare the request parameter to the model and get all the necessary inputs with the sensible defaults. Again we are gonna print or log the request details. This is basically for debugging purpose, because usually at first go sometimes you don't get the exact response, so you need to log everything so that you know what's going wrong and you can fix at that moment of time. So that's the reason I've written this print processing the text, and I have tried to log what text and what language I am sending to the model. Then I'm checking if there is a text or whether it's empty, whether it is received the text from our, and then we return. If the text is empty, then we return the response in JSONify format. This also prevents processing empty requests and provides meaningful error messages. Then we check if the language model, then we validate the language support and ensures we only attempt to use the languages we have model for. So this is another condition, and then once we do that, I have created one more function that this if this should be translated, which we are getting as true when we select the option. So basically that determined whether this particular function should be translated or not. So we are using translate if needed, and then if it is translation is needed, then we will try to call the text to speech model by knowing which language it needs to be converted in, whether Spanish or whether German or whether French or whether Hindi. So with this if condition it knows, and it also handles the operation of translation before TTS, and allows user to translate the text before speech generation while gracefully handling translation errors. So I have done the same function twice. Either the major reason is I've just created one more API just to get the text in different format, if in case I want to build the application in more advanced format. But here I have reused the same logic so that it un- to avoid unnecessary translation of the text if it is not needed. That's a reason I have added those condition. Then it translates the text, and it does the same thing which I've explained before, and then it throws an exceptions if the translation error happens. Next we get the model and the tokenizer for the requested language model. So get this is basically we're getting the correct language specific model for speech generation. After that we are going to convert the text into tokens the model can process. So for that we will just print the tokenizing as a text. This is basically logging it. Then we are going to get the input for by converting the text into tokenizers, and then print those text which is got tokenized. So the model basically understands the token. It can't directly process the text, so you have to tokenize the text before you pass it to the model, and then I've just logged it to see how these tokens look like. After that we test whether whether the inputs which we have created, it is empty tokenized, or is it empty tokenized and the result has failed. Then we validate the tokenization output. We That basically catches the empty tokenization results, which would cause model errors basically. So we are basically catching if there is any empty response, and if there is an empty response, we would catch it beforehand before any the entire application fails in working. Now we convert the input tensors to long type. This is because the model requires the data in a particular format, and if it does not get that format, then again it might fail. So that's a reason what we are going to do is we are basically ensuring tensor datas are of data types are correct, and that VITS models which we are using requires long integer tensors, and incorrect data types would cause errors. So basically we are doing it as if torch is tensor bracket of input key, basically we're checking that, and then we are converting that input key value into long type for our model. Now let's generate the audio. So to do that, for generating the audio waveform, this is basically the core TTS functions using the model to produce the audio from the text. The torch.no_grad function actually improves the performance, since we do not need to track the gradient. So it's basically for performance purpose we have used that, and we are going to convert our input in the speech format by passing it into the model. As you can see, it's star star inputs, and these are the long data format which we have converted into, and then the output which you can see is stored in the output variable. Once that is done, we again check if there is any error by validating the model's output. By checking if the output value is equal to 0, then the output is anyway is going to be empty, and then we return the error message. So this way we are logging it, and we'll know whether the model is generating the response or not. Then we also check another error of audio which is generated successfully. We also check the shape out of it, which is useful for monitoring and debugging purposes. So we are checking just different formats of output, so that whatever we have got doesn't have any error. So, and if there's any error, we can perfectly know at which part of the output we are facing the error. Now we are converting the PyTorch tensor to NumPy array, and the SPY5 wave writer requires NumPy arrays and not PyTorch tensors. This is basically required to create the wave file, which you can see where when I create generate speech, it creates one audio which you play, then it tells what speech it is there. So basically for that we are creating this, doing this particular step. So now you can see we are doing buffer equals to io.bytes.io, and then we are doing this spy.io.wavefiles.write bracket buffer comma rate equals to, we are passing the model config sampling rate, data equals to audio data, buffer dot seek equals to 0. So this is basically to create the in memory wave file and format the raw audio data as a standard wave file without writing to the disk, basically, so that I just could show you the output, and this audio won't be saved. Just for anyone who wants to understand or how this could be, if you're getting an English message, what it means in different language, you can just paste it, it creates a wave file. Now it will be, after doing that, we will send the audio files which we have created whenever the API is called. So basically we are doing the return send file in which we are passing the buffer, the meme type, which audio or wave, and as an attachment true, and download name is equal to generated speech dot wave if you want to download it. So this is how you return a audio wave file for the response which you get from the model. So which you can see when I show you that a wave file is created on which you play and you can hear the track record, so that way. And we also have an exception set for this also, to check whether the information is sent correctly or not, or what issues we are facing when we are doing this. So we are basically creating an exception as E, and we are passing the detailed error whichever there is there in the track file. Then we are importing the trace packer file. So this is one of the library which provides you a very compressive error handling. Then we check what all traceback formats are there inside that. Then we return the JSON format of the error response. So basically catching all the exceptions, log details, error information for debugging, and returning appropriate error responses. So then we are going to define if name entry point for application. So as we know, we have created two functions. Now to enter this Python applications, there has to be some entry point or the start of the Flask development server. So we write name if equals to name equals to main, and then it runs the application where when the script is executed directly, specifying the port as this. To access our server, the port number is 3000. You can put whichever port you want, which you if 3000 is occupied by some other service, then you can use 3001. So, and also enabling the debugging mode for the port. So this is the main place where you actually start or basically make your entire server part run at 3000 port. So this is the entire backbone of how you can use the model and pass the text or convert the text in different languages, or also create a text to different languages API in the server and access it. So this is the core base of how you can create your own version of application for text to speech. Now let's understand how it is connected to the front end in the next part of the code.
Hola, mi nombre es Ámbar, estoy aquí para ayudarte con cualquier cosa que necesite, ya sea que estés explorando nuevas ideas, resolviendo problemas o simplemente curioso sobre algo. Sumamos juntos.
So now let's understand how our backend communicates with our front end. So for this we have made an API call in our front end called in the file app.jsx, and as you can see, I have created a constant called as generate speech, inside which I am writing try and catch, so that if there is any error it doesn't break the entire system. So first we are going to check is that the HTTP post request to API endpoint, it is sending three pieces of information: text, language, translate. So the text is the content we want converted to speech. Then the language is the code like EU for American English or any other language which we want it to get translated, and a boolean flag is set to true indicating we want translation capability. So these are all the inputs which we are going to send from our front end to the back end. Then after that, I have done an error handling which checks if the response is not okay, then it will throw an error and it will check or parse the JSON error response and throw an error with the specific message from the server or a default message. After that, it will process the audio response and we convert the response to a blob object which represents the audio, and we create a URL for this blob using url.createObjectURL, and we save this URL to our application state via speech URL, and then we also do a catch for it to check if there's an error or not, and we log the detailed error by doing console for debugging, and we display a user friendly alert if there is any error in loading the file or something. We set is loading to false, indicating the process is complete, and this would typically be used to control the loading indications in the UI context. So the code which appears to be a part of React component is indicated by this state management, that is speech URL or set is loading, and the complete component would include state variable for the text, language, loading state and speech URL, a form for user to input the text and a select language, a button to trigger this function, a audio player to play the resulting speech. So in the conclusion, this is how the entire application we have created if for the text to speech integration. In a nutshell, this approach provides a clean separation between the front end and the speech generation service with the proper error handling and state management throughout the process. So the API is to note, the API endpoint is set to local host, so this would only work in a development area. For a production, you would have to update the URL to your deployed speech API endpoints. So in this entire tutorial, I'll be just focusing on the main core part. If you want to know about how the React component works or how each component can be built, please enter in the comment section as UI, and I will make another tutorial for the front end part. Thank you so much for watching the Lingua Flow tutorial. If you found this helpful, please hit the like button and subscribe to Minds of Machine channel for more AI development content. Cannot wait to see what amazing multilingual applications you will build with this technology. Until then, see you in the next tutorial. Bye bye.